I'll get started here in about a minute or so while people are still trickling in. As always, if anybody has any logistical type questions, anything right now, I can answer it before I get started if there's anything anyone wants to ask me about.
Hey Chuck, one really minor question is that sometimes when I save the RMD file and HTML file to my desktop, there's a .r history file.
Yeah.
That's something you can just delete and is not important, or is that?
That's not really important. So that just means that your RStudio is set. So if I pop open RStudio here, it means that up here, it's probably set to save a R history file, like always save history here or something like that checked. It's not really necessary. The history files are not super useful in R. It basically just logs any commands that were run in the console or whatever. It's the same thing as this history tab over here in RStudio. It's not the most useful thing in the world. I would probably just turn it off so you're not creating useless files.
Okay, great. And in terms of just general best saving practices, as you mentioned in a previous session, at creating projects within RStudio and then just saving files to your own desktop like you do with other programs are just kind of the two best practices.
I'd create projects and you save everything within that project. So keep it in its own subfolder. So basically, I mean, I'll show you like the sort of structure that I do for saving things. So for instance, all of my individual projects, not quite all of them, but a lot of my individual projects are in like central project folders like this. So these are this is a mix of different websites, different workshops, different classes I teach, and a few journal articles mixed in here. So there's sort of like just a million different things in here. And I might pop open like a random project, like my campus policing project here. And in this particular one, I basically have a project folder and then subfolders for syntax files contain all the individual R code files necessary to like generate the journal article. The documents folder, it looks like I have everything in syntax. Oh, this is camps police and this isn't for a journal article. There's no docs folder here yet because I haven't done any documents. Presentations, each presentation will get its own subfolder and the relevant files are in there. That kind of thing. Everything should be its own subfolders. Things should always be in the same sort of places. Yeah, so that's how I tend to arrange things. Saving things to your desktop is a good way to permanently lose things or end up with 10 million things on your desktop. Same thing with a documents folder. Like you shouldn't probably be saving anything top level documents folder. My documents is probably littered with random crap, but actually I don't even have any projects in here. Everything's on my OneDrive or my Dropbox for me. Mostly like in GitHub here, though I have some secondary project folders for things too large to put online. But that's sort of the organization I would do is just every single project or class. So for instance, this class has its own folder right here, and then these are all the assets for it. If somebody happened to go online and look at the GitHub for the class that we're in right now, CSSS508, you'd see every one of these files here is just what's in the GitHub directory that any of you could download. It just mirrors the stuff off my computer onto GitHub. But everything gets its own folder.
Cool. Thank you.
Okay. So I will get myself started here. Cancel this out here. So first thing, does anyone have a guess for what a pirate's favorite programming language is?
R.
Good guess, but 'tis the C. Yeah, I hear for the bad jokes. Okay, so today's lecture, week 4 lecture, is R data structures. So the first 3 weeks of this course, I set you up with like cool toys. So I set you up with R markdown documents, I set you up with visualization, then I set you up with dplyr for data manipulation. The thing is that gets us pretty far, but you may and probably often will need to get deeper into the weeds of programming with R because you won't be able to do everything you want to do with sort of the dplyr syntax we have, sometimes even the ggplot stuff we have for doing graphics. I mean, often we're going to be working with types of objects that don't make a nice rectangular data frame, where you need to create some intermediate thing that isn't a data frame. So what we're going to get into is sort of data types in R. What are all the different structures of data? How do they work? How do they relate to each other? So this is sort of a foundations and fundamentals one. So the way that I structure this class in general is I usually start with something cool and interesting, then I go to the fundamentals, and then I will return to cool and interesting things. This course is the same way. I start with the cool, interesting stuff at the beginning, then we have sort of some mixed weeks of sort of foundational material, and then we're going to finish off again with cool and interesting stuff like mapping and reproducible research and stuff like that. So today it can be a little bit of a slog, but it's sort of core things that will probably help you understand better why things in R work the way they do, that you've sort of maybe intuitively grasped or not grasped up to this point. Okay, so things we know up until now. So I've said a couple times, I think, that data frames, which kind of look like a matrix, they're a big rectangular thing you store your data in. They have columns that usually have names, and they have rows, right? A data frame is not a matrix, but rather it is a list of vectors, each column being a vector. Those vectors sort of form the columns of the data set, right? They are vectors that all have the same length. Each of those vectors has the length of the number of rows in the data frame, okay? But data frames are a list object. To know how to do everything we'd ever want to do with a data frame, we're going to need to know how to work with lists also. Okay. And even if we know a lot about working with data frames, they're not the only object we're going to want to work with in R. For instance, you might want to get stuff out of linear regression output. Linear regression's output is a list and not a data frame. You can convert chunks of it to a data frame, but the whole thing itself is a big list. Okay. So we need to learn about other object types in R. We need to learn about vectors, matrices, and lists, so we can do all these different things that we can't do inside of dplyr. Okay. So, vectors. So, what are vectors? In R, we just call any set of values of the same type a vector, right? We can create vectors. One way we can do it is with the C function, which stands for combine or concatenate, which we've used a bunch of times so far. If I want to create a vector of the numbers 1, 3, 7, and -0.5, I could just put those numbers separated by commas inside this C function, and it generates this length 4 vector. Okay, this is just making a vector. Vectors only have one dimension. They have a length. If you want to know the length of a vector, you can put that vector inside the length function, and it will tell you how many elements it has. Okay. All elements of a vector are always the same type. That is, they are all numeric, or they are all character, or factor, or integer, or logical, and we're going to talk about these different data types. If you mix character and numeric data in a single vector, the vector that results will just be converted to character, okay? The way R works is that it will convert, if you mix data types, it converts the entire object to whatever is the least complex data type required to store all the information. If you have text in it, the least complex data type is going to be character. Okay. So when you do like arithmetic, you do math on vectors in R, R will do this element wise. Okay. So if I take the vectors 1, 2, and 3, and 4, 5, and 6, and I add them together, it will add 1 to 4, 2 to 5, and 3 to 6. That is the first element plus the first element, the second element plus the second element, the third element plus the third element, giving us 5, 7, and 9. Okay? It's doing them element by element. If I do something like exponentiation here, it does 1, 2, 3, and 4 cubed. It will cube each of them individually. It won't do some operation on them all simultaneously. It kind of treats them all like their own individual numbers. Okay, common operations that sort of behave this way in R that are element-wise are all the normal mathematical operators and most functions too. Things like taking exponentials, taking logs, all that kind of thing. They'll operate each element one at a time in the vector. Okay, so something that has been happening every time we do an operation with vectors in R that you probably haven't even noticed or had to think about is vector recycling. So if we work with vectors of different lengths, what R will do is it will recycle the shorter one by repeating it over and over again until it is the same length as the longer one. So if I take the vector 0.5 and 3 and I multiply it by 1, 2, 3, and 4, what it's going to do is it's going to multiply 0.5 by 1, 3 by 2, then go back to the beginning of this shorter vector, 0.5, multiply it by 3, multiply 3 by 4. right? This is kind of an odd thing. It's called vector recycling. So it means this statement up here is identical to this one down there where I've just taken 0.5 and 3 and repeated it again. You'll see the results are exactly the same. What you probably haven't realized at this point is that you've been doing this all of the time in R. If I go back to over here where I did exponentiation by 3, this would be exactly the same thing as me taking a vector of 1, 2, 3, 4 and exponentiating it by a vector of 3, 3, 3, and 3. It's actually recycling this length 1 vector to be the same length as this, and then doing element-wise operations, okay? So this is the way R handles objects of different lengths when they're vectors and you're doing operations like this. It will take the shorter one and expand it to be the length of the longer one, and then do the operation. It's just that if the shorter object is a single number, it just repeats that single number all the way down to be the same length as the longer vector, making it kind of look like we're not doing vector recycling, okay? Does that make sense? We're gonna see some consequences of this. Okay, so like I said here, scalars, a single number like this, are a special case of recycling. If I do 3 times a length 4 vector plus 1, this is a length 1, this is a length 1, but the result is going to be the length of the longest object, because the 3 here will be extended to be length 4, the 1 will be extended to length 4, and then it's going to create this vector like this, which is the result of taking 3 times -1 plus 1 is -2. 3 times 0 plus 1 is 1, and so on. And you'll see R obeys conventional order of operations. It does the multiplication first, then the addition second. If you want to control that order of operations, you can put things in more parentheses, and it will obey the parentheses to do that, okay? So you can do vector recycling on things that have incommensurate lengths. That is, a larger object and a smaller object which they don't evenly like multiply together or divide into each other to be the same length. So for instance, a length 4 vector and a length 3 vector can be added together, okay? But the recycling is a little bit weird, and R gets slightly upset about this. It's gonna kick a warning like this. Warning in 1, 2, 3, and 4, and 0.5, 1.5, 2.5. The longer object length is not a multiple of the shorter object length, but it will still produce a result. But the result is slightly strange, because what we get is 1 plus 0.5, 2 plus 1.5, 3 plus 2.5, and 4 plus 0.5, because it wraps around to that one. Okay, this is what R will do. But try not to let R catch you by surprise with this. If you want to be recycling, that's real nice, and it's a good practice to save typing sometimes, but it can be better usually to be safe and make sure the objects on both sides of the operator are the same length, or one of them is length 1, because that's kind of hard to mess up, okay? If you get tricked by this, weird problems can arise, right? If you've got something like you meant to take a vector of length 100 and you added a 99 to it, you've got one value wrapping around in a weird way. This can cause strange results. Okay. So, vector-wise math. Some functions will operate on an entire vector and they'll return one number rather than working element-wise. These are things like sum, maximum, mean, median, standard deviation, right? If I give a length 4 vector here into sum, I get 10 out. If I give this a length 1 million vector, I'm still going to get a single number out of it, okay? No matter what I do, sum returns a length 1 vector, max always returns a length 1 vector, okay? Some functions you would think would return a length 1 vector, but don't always. An example of this is functions that return the mode, because you can have multiple modes in a vector. It will often produce one number, but sometimes produce multiple numbers. To use something in dply or summarize function, it needs to take a vector and return a single number. You wouldn't want to use mode in summarize because it might unpredictably return 2 numbers if it's a bimodal vector, okay? Questions about that? Pretty good. We've seen these before. Okay, so here's an example of something you might want to do that before you might not have realized involves a bunch of recycling of vectors. So let's say we had some test scores and we wanted to put these on a standardized scale. So the formula for standardizing something that is producing a z-score is z is equal to each individual value of x minus the mean of all values of x divided by the standard deviation of all values of x. We can take this exact formula here and in R just do that same math. So let's say our test scores are these 13 values that look like this, and we want to standardize it. So if I want to standardize it, I would take x, that is each individual value of x, subtract its mean, and divide that all by its standard deviation, okay? Now what's interesting about this, if you think about it, x right here is 13 numbers. Mean here is one number, and standard deviation is one number. So what R is going to do is it's going to make mean of x, the mean of x, repeated 13 times, so it's the same length as x. It's going to take SD of x and make it repeat 13 times, so it's the same length as this. I produce z, round my values, and I get 13 values out, the length of the largest object in this particular calculation, that being x, okay? That's the way R does these things. It's hidden from us most of the time. We generally think of this as being a single number, this being a single number, and they are in isolation. But as soon as you put them in math with a longer object, they get expanded to be something longer also, okay? So vector recycling. If you didn't want to manually standardize like this, you could do this with the scale function in R. It performs the same operation, but it's a little bit more flexible, though its output is sometimes weird because it provides metadata too. Anyway. So, any questions on recycling before I hop along? We're going to get into data types next.
Are there any other like big holes that people tend to fall into? Because it seems fairly like straightforward and simple how you just laid it out, but like I just don't feel that it probably is that straightforward and simple.
So what do you mean? So you mean with the vector recycling specifically, or
yeah, with vector recycling, if you're going to end up using it, like you talked about possibly having two vectors that didn't divide easily into each other, are there any other kind of like common things people run into without even realizing it that we should be aware of?
So the thing is typically no. The thing with vector recycling is usually instead of it causing problems, like most of the time it doesn't cause problems because most of the time if you're using vector recycling, it's with a single digit or something like that. The normal time it will run into a problem is if you weren't I'm trying to think of common vector recycling problems. The normal one is when you have things that are of incommensurate lengths, but that provides a warning. So you usually know it's happening. The other one that sometimes people get into is they don't realize that one of their objects is greater than length 1 or something like that. Like they don't realize they're recycling something, they don't intend to, but that's not something specific to recycling. That's more like not knowing how long your input objects are. Really quickly, I want to show one of the things that's useful about vector recycling. If I do something like, let's go x equals 1 to 20 in a data frame, z equals like 1 to 2, I can get a data frame here that is the numbers 1 to 20, and then z repeats 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. This kind of thing is really nice for setting up little toy data frames to do things, or maybe like setting up, we'll get to this later, but setting up counterfactual values to do certain types of estimation and things. I find this stuff to be, so for instance, I could do k equals 1 to 4, and it just is automatically recycling these things to be the same length. This is a way you can quickly generate sort of permutations of different values to perform special operations and stuff. Recycling can be really useful. It might not be apparent to most of you how that's useful, but if you spend more time programming, you'll be like, oh, that's really handy. Get there. Okay.
Is there an issue where you're expecting something to function like matrix algebra? So you have like two different lengths of things, you maybe want to like multiply them together and it ends up functioning like this as opposed to not working because it...
Yeah, well, that's the thing in R is that if you're expecting, we're going to get to this with matrices in a bit. I'm going to talk a bunch about matrix multiplication and things. So we'll see. But yeah, if you're expecting, for instance, taking two vectors and multiplying them together to give you a matrix operation, it ain't going to happen. But there's just different operators to do matrix operations. So we'll see them in a bit.
Perfect. Thanks.
Yeah. Okay, and in fact, there's 2 homeworks for this week. One of them involves a whole bunch of matrix math for people who are into that. The other one is more straightforward. Anyway, okay, so types of vectors in R. So if you want to know what type of vector you have, that is what type of data are in it, you could use the class or structure functions on it, okay? So here's a few different types of vectors. So there's numeric vectors, which we work with really commonly, right? Numeric vectors could be any type of numeric data in R. If there's no text in there, it's probably a numeric vector of some kind, right? So a thing about numeric vectors here is that R is perfectly happy for me to include an equation in here, not an equation, but a actual algebra in here, and it just treats this as the number 30 in this case. So you can make a numeric vector that contains some math operations and stuff. It's still a numeric vector because the result of this calculation is numeric, okay? So you can have some symbolic elements and it's still numeric, as long as it ends up being a number at the end. Okay, so numeric vectors contain any kind of numeric data up to some level of precision. You can have a lot of decimal points in things in R. You're probably not going to run into too many numerical precision problems, but numeric vectors. A special case of numeric vectors are integers. Integers are just vectors which take whole number values only. If you're working with incredibly large quantities of data, integers take up less space than numerics, so you can sometimes save yourself. If you're working with, if you're somewhere in the hundreds of billions of rows of data, storing integers as an integer data type over numeric might save you gigabytes. Just something worth knowing. Yeah, character data contains text. So a character vector like here, red, blue, yellow, blue, whatever, this is character data. R doesn't care what is inside this character data. To R, this is all just text. You can't do any math with it. You can't do any kind of operations with it. R is just like, this is something I don't know how to deal with, so you can put whatever you want in there. Okay, character data is basically the most complex data type in R that's commonly encountered. You can store anything in a character vector at all. So a character vector, sure, I have words here, but I could have each element could be a sentence. Each element could be an entire book up to the storage limit for a single element in R, which is pretty large. Factors look kind of like character vectors, but they're really their own separate data type, okay? So I could take the character vector I create on the previous line and make it a factor by putting the factor function around it, but factors are a little bit different, okay? So factors are a type of categorical data with an underlying numeric representation. Basically, it will convert each one of the unique values in it to a level, and then the actual data will be stored as integers corresponding to the levels. We'll talk about these kind of at length. Last common data type I think I have in here is logicals. Logicals are just binaries that take either a false or a true. They are the simplest data type in R, and they're generally produced by logical expressions. Okay, so.
A quick question.
Yeah.
What happens if you put a variable into a vector? Is it just the type, whatever type the variable is what
So when you say, what do you mean by put a variable into a vector?
So if you like stored 10 times 3 into X, and then you could you have X be in that vector as 10 times 3, or would it
yeah, you could.
X?
So the interesting thing about that is if you do, you make X equals to 10 times 3, and then you put X in a numeric vector and assign it to something, the numeric vector will have the result of that calculation. If you go and change X after that, it will not change in the vector that you created.
Cool.
Yeah, it's not a pointer. Yeah. Yeah, R is unlike a lot of languages where if you create a variable or something, if you change it later, it changes the state of it in every other object. R actually resolves all of its calculations when it assigns things into objects, so everything is static. So for programmers, very important. For everyone else, it's okay to be scratching your head and be like, I don't want to know about that. Okay, so generating numeric vectors. So numeric vectors contain only numbers with an arbitrary number of decimal places, okay? There's shortcuts for generating common vectors you might want to use. Sequences are really common. Let's say I want the sequence beginning at -3, finishing at 6 in increments of 1.75. That's the syntax there. sequence from -3 to 6 by 1.75. You'll notice here it begins at -3, but it finishes at 5.75 because that is as high as it can go without passing the second number given to it. So you can generate sequences with arbitrary spacing this way, okay? Another thing you might want to do is take a single vector like -1, 0, 1 and repeat it multiple times. I could say repeat this vector 3 times and I get -1, 0, 1, -1, 0, 1, -1, 0, 1, right? It just repeats this thing over and over again. An alternate argument to times and repeat would be take the same vector and say each one 3 times. Then it would repeat the first element 3 times, the second element 3 times, and the third element 3 times, okay? These are sort of like convenience functions to generate numeric vectors, should you need them for some purpose. So the colon operator that we've been using to generate like integers over it is just a shortcut for sequence the first number colon the second number, and it defaults to by equals 1. So the colon operator just calls on this sequence function. Okay, so generating integer vectors. Integers are just a special case of numeric vectors where all the values are whole numbers, right? They can still be treated and converted to numeric stuff on the fly. So the quickest and easiest way to generate integer vectors, especially if you want sequences, is to use the colon operator. So the colon operator just works where you take some number you want to begin counting at, colon, a number you want to finish counting at. So I just demonstrated here that I could put 1 colon 12 here, but I could also assign 12 to n and use 1 colon n just is the number 12, so it works the same way. The colon operator doesn't require like literal numbers here. You could use an object, which is a single number. And then 1 colon 12 generates all the integers from 1 to 12. You can also count the other direction. This is counting from 12 to 4. It will count downward, okay? Good way to create indices for things, okay? You can also specify a single integer. You can also do this in a vector. You can specify integers and make them the integer data type rather than numeric by saying the number and following it with L. Okay, you might ask, why is it L to specify an integer in R? I too ask this because it doesn't make any sense. It's just the way our syntax is. I forget what the arcane reason in the like S language, which is a very old language dating back to the 80s at Bell Labs or wherever. L is just what they use to designate a vector, or not a vector, but an integer. Okay, so if you need something to be the integer data type, definitely write the number with an L after it. There you go. And you can tell it's still numeric because it turns orange or whatever is your highlight color for a number. Okay, it's just weird because you have an L there. You're like, shouldn't that be character? No, it's just a weird indicator for integers. Okay, so character vectors. Character vectors store data as text, and they come up a lot for the social sciences here because this is a class for the social sciences. You probably have a lot of character data in the stuff you work with, all sorts of survey question answers, things like that, names and IDs and addresses and all that, okay? They tend to come in as character data, okay? So an example I might do is I create a vector called first names, and it's these first names, Andre, Beth, Carly, and Dan. If I get class of first names, it's character, okay? You can store numbers as character data as well. I could say Andre, Beth, Carly, Dan, 45. And I could put the number 45 there with or without quotes, and it's just going to become character data. The thing is, if you have like 45 in quotes as character data, it might look like a number to you, but R treats all character data as character, and you can't perform any math with it at all. Okay, if I converted this vector with 45 at the end to numeric, it would make all these text ones NA and then turn 45 to a number. Okay, there's no way to convert text logically into numeric values. Okay, so factors are categorical data that will encode levels of categories into the vector itself. Okay, examples of things you would often store or use as factors are like sex or gender, membership in an experimental group, or geographic region for your data. So I could take a vector like this of MFFM, make it a factor, and assign it over here to sex. Now you'll notice the display here is not quoted, MFFM. It kind of looks like numeric values here. It's not quoted like character data would be. And then it has this additional thing it prints down here, which are the levels, okay? So in factors, it will display the levels here. They are in order. This is level 1, this is level 2, and so on, which means under the hood, this thing is the number 2, this is the number 1, this is the number 1, and this is the number 2. So if I convert this factor to as numeric sex, what pops out are the factor levels. M is the second level, so it gets converted to a 2. F is the first level, so it gets converted to a 1, and so on, okay? Factors have an underlying numeric representation. So if you take a character vector, convert it to factor, and then convert it to numeric, you will get numeric values. They might not be what you're expecting, but that's what you'll get. The thing is that character data like this kind of categorical data, cannot go into statistical models and things like that directly. One way or another, it needs to be a factor. If you give a vector of character data to something like a linear regression model in R, it will convert it into a factor automatically, okay? And the way linear regression and other models in R works is they will make the reference level of that in the regression whatever is the first level of a factor. We can change the levels of a factor, and that lets us control what is the reference level in a model. We'll see an example of this later. Okay. Why would it not code it 0, 1 instead? This is a great question, and the reason is that R begins at counting everything at 1 instead of at 0. So every other programming language you're likely to encounter starts counting things at 0, and that is because most programmers think in terms of a Cartesian plane. The Cartesian plane center is at 0, 0, and you start there and count outward from it. R was designed by statisticians who begin counting at 1 instead of at 0, and so factor levels also begin at 1 because everything in R starts at 1. Okay, so here's another one. Why does it convert F to 1 and M to 2 since M comes first in the vector? It converts the levels based on alphabetical order instead of the order they appear in the vector, okay? Do you know a serious problem with that? Different languages have different alphabetical orders for some letters, which means if you're in one locale with one language and another locale in another language, and you convert them to a factor, you will get different factor levels between those places. Good to know. Doesn't come up too often. Every once in a while it does, though. Good example of that is if you're like natively working in Cyrillic or something in your computer, the character that looks like a C to us is an S in Cyrillic. They're in different orders in the alphabet. Okay, it's a rare error you'll probably never encounter, but if you do, it will drive you insane. It makes some things not reproducible. Okay, so logical vectors, okay? Logical vectors take only true and false values, and they're usually the product of some logical test. So we usually generate one not by writing a whole bunch of trues and falses, but doing some test that produces trues and falses, okay? So for instance, I take those first names I looked at before, right? The first names were like Andre and Beth and Carly and Dan, okay? I could get the number of characters in them. I'm going to assign this to name lengths. So the names were 5 characters, 4 characters, 5 characters, and 3 long. I could then create a logical vector by saying name lengths greater than and equal to 4. Okay, well, this one is greater than or equal to 4 because 5 is greater than or equal to 4, 4 is greater than or equal to 4, 5 is 2, 3 is not. So this produces a true, 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 and false. This is all that's happening inside filter statements in dplyr. You give it a logical statement, it produces a number of trues and falses equal to the number of rows in your data. It keeps the rows that line up with a true, it drops the ones that line up with a false. Okay, we're just making logical vectors. Okay, you can do math with logical vectors though. The reason for this is that true is the number 1 and false is the number 0. So unlike counting and factor levels, false is still 0 and true is still 1, like in most programming languages, and binary is a language in general. Okay, so if I do that name lengths greater than or equal to 4 and get true, 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 false, I could take the mean of this, which is name lengths greater than or equal to 4. What is this 0.75 then? Anybody know? I'll wait.
Is 1 true? Is true coded as 1 and false coded as 0?
Yes. So that 0.75 is the proportion of trues that were in that vector. Thus, that is the proportion of names that were greater than or equal to 4 characters long. Okay? So this is sometimes a useful sort of operation to do. You can create some sort of logical, take a mean of it, and that gives you the proportion of trues you'd find in it. So sometimes it's useful to do numerical operations on logical vectors like this. We're going to do a bunch of these in different examples in later lectures. There may be one here, but this can be kind of a handy operation to know. Trues and falses are also numeric or can be handled as numeric. So you can do some fun stuff with it, like take some of them to count the number of ones. Okay. So it's the proportion of name lengths greater than or equal to 4. Okay. So combining logical conditions. Suppose we're interested in which names have an even number of letters, okay? So I could create a vector which indicates whether the names are even in length. What I say here is name lengths modulo 2. So this is the modulo or modulus operator. This is a common programming one and a sort of operator you would never have seen probably doing normal algebra and math in like high school or something. You might have seen it in college level classes. So this just says take name lengths, which is a numeric vector, divide it by 2, but return the remainder of it, okay? So if I take name lengths, divide them by 2, and check that the remainder is 0, this is a way to check if name lengths are even, because something can only be divided by 2 and have a remainder of 0 if it is an even number, okay? We'll see some examples of this. This might be a handy one that comes up once in a while. So this is now a logical of whether or not those names are even in length. If I say even length, false, because Andre was a 5-character name, true, because I think Beth there was a 4-character name, false, and false. So this is the only even length name in our names, okay? I could also be interested in names whose second letter is A. So I'm gonna say second letter is A, assign to that substring first name. So what substring does is it's going to go into the vector I give it like this, one element at a time. It's going to begin at whatever I say start. So it's going to go to the second letter in each element. It's going to stop at the second letter of each element. So this substring first name start to stop to gives me the second letter of every one of those names. I then test to see if that is equal to A. So thus, this statement over here is a bunch of falses or trues on whether the second letter of each name is an A, okay? If I display it, you'll see it is false, false, true, true. Carly and Dan have A's in the second place, okay? Makes sense? Doing some odd little operations. So we see here that even length is false, true, false, false. Second letter A is false, false, true, true. We could combine these together. So the AND operator with logical operators requires that each element in the same position be true for it to produce a true. So if I say even length and second letter A, if we remember, this one over here is what I think it's, yeah, false, true, false, and false. This one is false, false, true, true. There are no trues in the same position in these two vectors, so everything that comes out is false. For any of these to produce a true, element 1 would have to be true, say, in both this and this. Element 2 would need to be true in this one and this one, but that's not true in any case, so this is all falses. On the other hand, I could instead use OR. And OR says if at least one element in that position is a true, it will return a true. So if we remember, neither even length nor second letter A had a true in its first position, so it produces a false. But the second name was even in length, and the last two names had a second letter A, so I get false, true, true, true. So this is the way that the AND statement and the OR statement actually work, okay? If you think of them numerically, it's kind of multiplying, this is kind of multiplying your logicals together. Over here, it's not exactly adding them, but it's somewhat similar to adding them and taking things greater than 0, okay? Then we could use the exclamation point or bang operator to switch trues and falses. So if I say even length or second letter A, Remember, that's false, true, true, and true. If I put an exclamation point in front of it, it makes the false into a true and all the trues into falses. Okay? Exclamation point just flips logical conditions. Make sense? These are things to play with to get some comfort with. Okay. So, subsetting vectors. Okay, I'm going to move on from vector types and logical. So if you have any questions about them, ask them now. Otherwise, I'm going to get on to subsetting and working with them. Okay, so subsetting vectors. Okay, we can subset vectors in a number of ways. One way is that we could pass a single index or vector of entries that we want to keep from that vector. So for instance, I could say first names and then give it the vector 1 and 4. This will give me the first name and the fourth name. Okay. If I said C 1, 2, 3, and 4, it would just give me the entire thing because there's 4 elements to it. You could also pass a single index or vector of entries to drop. I could say, take the first names, but subtract the first and fourth name, and I'm going to get the second name and the third name. Okay, so you can do positive indexing or negative indexing. This is kind of like selecting things in dplyr. You can do either positive indexing or negative indexing, but you can't do both because they're mutually exclusive. Okay. You can also pass a logical vector to names, okay? So if you pass a logical vector, the logical vector must be the same length as whatever you're subsetting. So if there's 4 elements in the vector you're going to subset, the logical vector must be length 4 also. And then what it's going to do is it's going to keep the elements that line up with a true and drop the elements that line up to a false. This is how the filter statement in dplyr works. If I say, take the first names and then subset so they are either even length or second letter A, I will get all the names that lined up with the combination of these two things. So if we remember, the combination of these logical statements was false, true, true, and true. This gives me the second, third, and fourth name because the first in this logical vector here is a false. Okay, so just drop the first element. Another thing I could do is I could say something like, give me the first names subset where sex, and if you remember, sex was just a factor vector I created earlier that takes M's and F's. It just so happens they lined up properly with the names because that's how I write my lecture slides. I could say sex is not equal to F. So what it's going to do is it's going to drop all values of first names where this vector sex not equal to F is a false. It's going to keep all the ones where it's a true. I end up with Andre and Dan because those two names lined up with the M's in my sex variable. Okay. And just to clarify here, there is nothing inherent that links even length and second letter to each other or even length and second letter to first names. These are even length and second letter are not properties of first names. These are just arbitrary vectors. You could subset on anything over here as long as it's logicals, and that would work. Okay, I'm not somehow extracting the sex of the name from first names. This is just a vector I created earlier that takes M's and F's as values. Okay. Okay. So some other logical and subsetting functions. So instead of typing lots of OR statements when you're working with the same variable, %in is handy for replacing many logical ORs. I could say first names %in and give it a vector over here, and it's going to return a true whenever an element of first names is any one of these 3 things, right? So this is 3 of the 4 names, everything except Beth, which is the second name. So first names %in Andre, Carly, and Dan returns true because this is Andre, false because this is Beth, true because this is Carly, and true because this is Dan. Okay, so this is a lot better than writing first name equals Andre or first name equals Carly or first names equals Dan. This is just a shortcut for that exact same statement though. Okay, another useful function for working with subsetting vectors is which. Which gives the indices of trues in a logical vector. So if I test over here this same first names %in Andre, Carly, and Dan, and I put this in a which statement, I get 1, 3, and 4. The reason for this is this says 1 was a true, the third element was a true, and the fourth element was a true. 2 is omitted here because it was a false. This provides numeric indices of trues, okay? Sometimes you're going to want numeric indices for things based on a logical, and which is the way to get it. Okay. So, missing values. We've used and seen missing values in past lectures. So missing values in R are coded as NA entries with no quotes on them in R, right? They are the color of a numeric value, but they are N and A. So here's a vector that has some actual values and some missing values. The thing about NAs is that, as I mentioned before, they poison the well for calculations. You will get NA out of calculations unless you remove your missings manually or with some extra argument such as NA.rm equals true in functions that have it. If I try and get the mean of vector missing here, because it has two NAs in it, I can't get a mean of it. You can't take a mean of something that doesn't exist, so it produces an NA. But if I say, take a mean of vector W missing NA.rm equals true, this says if it's an NA, remove it, okay? I can now get 3.6 because that's the mean of the non-missing values in vector W missing. Make sense? Okay. So a thing in R is that you can't test for something equaling a missing value. I can't say, let's find the missing elements in vector W missing by going vector W missing equals NA. The thing is NA is a missing value. You can't test to see whether something is something that doesn't exist, okay? I can't say it's equal to NA because NA isn't something could be equal to. It is the absence of a value. Instead, if you want to find NAs in a vector, you use the is.NA function. So I say is.NA, vector W missing, and it says false, false, true, because the third element was NA, false, 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 and the last element was NA. So this is a way to get a logical that finds all your missing values. Now, I can show you how NA.rm equals true actually works in the mean function. What it's actually doing is taking vector W missing and then subsetting it to the values that are not missing. So it takes vector W missing is NA, which would produce false, false, true, false, 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 and true, puts an exclamation point in front of it, which changes it to true, true, false, true, 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 false, okay? Subsets the vector by that, which results in dropping all of the NA values, and then it takes their mean and gives you 3.6, okay? So all NA.rm equals true is doing is this subset operation over here on the vector. That's how it works. It's just using some logical subsetting, which you could do yourself manually if you felt like it. Questions? Okay. So a weird thing about R, right? Well, I shouldn't say the weird thing yet. So like I said, if you're testing logical conditions here, NAs produce an NA rather than a true or false. If I say vector W missing equals 5, it will give me a false and a false in the numeric values that are not 5. Where it's an NA, it will give me an NA. Where it's a 5, it will give me a 5. Okay, it makes sense. I can't test to see if this left side over here is an NA equal to 5 because there's nothing there to test. NAs aren't there, okay? A weird thing though is that if I use %in instead of equals, it will still test against NAs. This is an oddity. If I say vector W missing is in the number 5, you'll notice the NAs, they now produce a false, the 5 still produces a true. This is an oddity that even though this thing, which is normally equal to sort of multiple equals statements, it can check for missings, but equals can't. So you can kind of use %in instead of equals in cases where you have NAs if you feel like it. Hardcore R programmers will get upset if you do this because they're like, no, you should manually remove your NAs, but this can be an operation useful as a shortcut, okay? So I can also, however, with NA, with %in, you can actually test for NAs too. I can say vector W missing %in NA, and it will find the NAs this way, just like the is.NA function. So %in, it's usually used for checking if something equals something in a vector on the right side, but you can also use it for some shenanigans involving NAs. So %in is a nice function to know about and make use of sometimes. It's a really handy operator. I don't actually know why it behaves this way under the hood, but it's nice to know that it does. Okay.
Chuck, quick question about the %in. So the way that we can think about kind of how to say %in our heads, essentially. So for the two equal signs, we can just read that out as tell me if x is equal to y. And then the %in, I've heard you say it as tell me if, you know, vector w missing is in this other value, but I've also heard you say is this one thing equal to this other thing? So
yeah,
what's kind of
%in is sequential equals. So what it does is you can say, is this thing in the thing on the right? But what it's kind of really doing is, does this thing equal any of the elements on the right? So it is kind of equals, but it's a sequential equals. It's equals over every single element on the right side. I like to say, is this thing in this thing? Because the language is easy because this thing is named in. So it's probably best to say that, but technically it's a sequential equals function. Okay. That makes sense? Okay. Okay. So sometimes you'll do calculations and you will get in positive or negative infinities or not a number from calculations. R is a statistical language, so it has values for infinities and for not a number, which are separate from NA values. So if you work in, say, Python, you're used to NaNs being used sometimes as missing values, other things like that. NaN is not a missing value in R. NaN is some value which is numeric but is not conventionally a number. For instance, the result of dividing by 0. Likewise, infinities are numbers. They're just not finite numbers, okay? You can get these from calculations. So if I take the numbers -2, -1, 0, 1, and 2 and divide them by 0, I get this sort of stuff, right? I get a negative infinity here, negative infinity here, not a number. 0 divided by 0 is not a number. 1 and 2 divided by 0 are infinities, okay? So you can check for these values using the functions is.finite or is.not a number, okay? If I say is.finite on this, it's going to return false for all of these because infinities, whether positive or negative, and not a number are not finite numbers. And I can test them with is not a number. This will return false and false because infinities are a number, but they're not finite. But not a number is not a number, okay? You might be like, when am I ever going to deal with infinities or not a numbers? If you write your own statistical functions by hand, the answer is a lot, because lots of things involved in different types of likelihoods involve infinite values on the lefts and right sides of the distributions. The normal distribution extends infinitely in both directions. You got to use those infinities. Okay. But most of you will probably never need these functions. Just nice to know they're there. Okay. So, like with data frames, we can look at our vectors or preview them, I say here, using head and tail. Okay. Letters is a built-in vector in R. Letters is the 26 lowercase letters of the English alphabet. If I do head on letters, I will get the first 6 elements of it. I could instead say head letters 10 and get the first 10 letters of the alphabet. I could say tail of letters and get the last 6 letters of the alphabet. Okay. We can also index vectors by assigning names to the elements of the vector. So if I create a vector that is the numbers 1 to 26, I could then assign to this vector of 1 to 26, assign to its names the capital letters of the English alphabet, okay? If I get a head on this vector, you'll see the bottom row is the actual numbers in the vector. So the vector is the numbers 1, 2, 3, 4, 5, and 6. But the elements of that vector are named A, B, C, D, E, and F the same way that columns in a data frame have names. Okay, so you can take a vector which takes single values and each element can have a name. What might you use this for? If I take a vector and then subset it to RSTUDIO, I'll get out 18, 19, 20, 21, 4, 9, and 15. These are the numeric positions of the letters I subset it by. You can subset vectors or anything that has a name by its names instead of its numeric positions, okay? It's really nice to subset something by its numeric position, or not by its numeric positions, but by its names, because if you rearrange that vector, no matter how you rearrange it, the names will follow those values so that your subsetting no longer depends on the order of it. If you have anything you're planning on rearranging in some way, its numeric indices will change for every value, but its names will stay the same, okay? This is a thing that's nice about subsetting by like column names in a data frame. You don't care what order the columns are in. You can always get the column from the right position if you call by names. But if you rearrange your data frame and you're calling on them by numeric indices, if that data frame moves around, what you get out of it changes. Okay? This is why it's highly recommended when you program stuff in R and also many other languages, do your subsetting by name whenever it's an object that could be mutable in some way. If it could be rearranged in any way, subset by names. So for data frames, you really shouldn't be using numeric indexing for like column names. You should use the names of the columns. Okay. So that's it on vectors. Do we have any questions about vectors before I move on to matrices? Okay. Here's a good question. How do you know when to use square brackets versus parentheses? So the interesting thing about square brackets and parentheses is they are totally unrelated. Square brackets like these are actually a function. They are the subsetting function. If I go into RStudio here, into my console and type $backtick bracket, I can get the help file on the bracket. So what the bracket is extraction or replacement of parts of an object. It is the subsetting operator. So these brackets like this, they are actually a function. They are an operator kind of like %in or the plus sign or the division sign or something like that. They are an operator or a function, okay? Parentheses, however, are not. I'm trying to think what it's even gonna give me if I do this. It's just gonna give me parentheses, okay? So parentheses are not a function. Parentheses are something used to provide arguments to a function. So for instance, here I say head parentheses a vector. This says a vector is an argument to this function. A vector bracket here says take this vector and subset it using whatever is inside. So brackets are always for subsetting. Parentheses, though, are used to determine arguments for every function in R. Does that make sense? Okay. Here's a question. What happens if when naming entries in a vector, the lengths of the vector used to name entries doesn't map up with the length of the target vector? Will it wrap around? No, it will not. R demands that your names be the same length as whatever you're naming. It will get quite upset if you try and name things using incommensurate lengths. It doesn't recycle for naming. Okay. And R really doesn't like two objects in the same like vector or data frame having the same name. Under certain conditions, it will allow it to happen, but it will cause many things to break down rapidly because R tends to do a lot of subsetting by names. If two things have the same name, it will return only one of them. Which one it returns will depend on certain conditions, but sometimes things will just break. It's usually really hard to make two things in the same vector have the same name though. Okay, anything else? Great, chugging along. Matrices. Okay, so matrices extend vectors to 2 dimensions. They have rows and they have columns. To construct a matrix manually, you can use the matrix function, okay? The matrix function will take as its first argument whatever you want to put in that matrix. So what I'm going to do is I'm going to make a matrix out of the first 6 letters of the English alphabet, and then you specify the number of rows and number of columns. If you provide a data argument like this, letters 1 to 6, you only need to provide either number of columns or rows because it can figure out how many columns or rows from the other one. If I say this is a 6-element vector, 2 rows, it's going to produce 3 columns. Okay, I specified both just to show you the arguments. If I say create a matrix, which is a matrix of these 6 elements, 2 rows, 3 columns. I get 2 rows, I get 3 columns. And you'll see it populates this matrix, that is, and it fills the values in column-wise. It goes A, B, C, D, E, and F, okay? If I instead want to create this matrix where it fills it A, B, C, I can say by row equals true, and it will arrange these things so it goes first element, second element, third element, fourth element, fifth element, sixth element, okay? These are otherwise the same function, okay? Creating matrices by hand. Okay. You can also make matrices by binding vectors together with the row bind and column bind functions, which are bind for rows, column bind for columns. I could say, take the vectors 1 and 2, 3 and 4, 5 and 6, and C bind them together. Each one of these vectors will become a column in the new matrix. So you see 1 and 2, 3 and 4, 5 and 6. So the 1 and 2 went here, the 3 and 4 went there, the 5 and 6 went there. So C bind takes multiple vectors and binds them together into a matrix. Row bind does the same thing with rows. If I take 1, 2, and 3 and row bind it to 4, 5, and 6, 1, 2, and 3 becomes the first row, 4, 5, and 6 becomes the second row of the matrix, okay? So you can manually assemble matrices from vectors or by populating them like I did here from a vector and saying a specific number of rows and columns. So if you need to manually create matrices, these are ways to manually create matrices in different ways. Okay. So subsetting matrices. We subset matrices using the same methods we use with vectors. The difference is there are 2 indices. Now there are rows and there are columns, okay? So I can say, take a matrix, give me the first row and second column, which is the letter C. So if I go back to a matrix here, the first row, this one right here, it's the, what did I say? First row, column 2 of a matrix is the first row. Shouldn't that be the column 2? Or did I create a new A matrix? A matrix, row 1, column 2. A matrix, oh yeah, row 1, column 2 is C. Yes, I confused myself by looking at a B matrix instead. Okay, so we can subset here. It's the same as vectors, but there's 2 dimensions. There's a length and not length, but there's a row and a column. Here's a question here. Will it recycle if you have extra columns and rows? So, oh, you're saying in creating a matrix, will it recycle? If you say, for instance, create a matrix using 1 to 6 here, but instead of saying n row 2, n column 3, I believe it will recycle. So if I stay here, create a matrix, but I actually want 8 rows, it will repeat that thing over and over again and vector recycle it to the appropriate length. So this is a shortcut again if you want some repeating matrix. I assume that's what you're interested in. The next one is, will vectors recycle if you have a vector that doesn't divide perfectly into the matrix? A vector of length 5 in a 2 by 6. Let's see what happens. It will probably get upset. Yep, the data length is not subsettable, but it will recycle it. So it will give you that warning about being unable to recycle it, but still produce the value. So the answer is yes, but it gives you the same error. Great questions. Okay, so next. We could subset this to say, I would like a matrix. I want its first row and its second and third columns and get C and E. So if you are interested in what the dimensions of a matrix are, there's a function for it. Dim, or dimensions, on a matrix will say it has 2 rows and 3 columns. So the order of these numbers is the same as the order you would subset in. Most matrix notation goes row and column, okay? The thing is, though, is if you do length on a matrix, it does not give you the number of rows and columns. Length on a matrix will give you the number of elements in that matrix, ignoring the fact that they are in rows and columns. The sneaky reason for this is that matrices are actually a vector. They happen to have rows and columns, but they also have a unidimensional length. So weird thing about R, everything's really a vector. Okay. So matrices sometimes spontaneously become vectors, okay? If you subset a matrix and it ends up having just one row or one column, it will turn it into a vector. So if I say a matrix, give me column 1, the thing that pops out is not a matrix with one column, it is just a vector of the entries in that column. If I want to subset a matrix down to a single row or column, but keep it a matrix, I say a matrix subset, comma, drop equals false, and it will keep it as one column in a matrix, okay? Now notice something very odd looking about this statement I just provided. I said a matrix, keep all elements, subset down to 1. This over here is not a dimension of matrix. Why is it that I can give a number here and a number here to subset, but this thing over here is not a dimension of matrix? It's like I'm giving some other argument to a function. This looks kind of weird. The reason for it is that these brackets here are a function like any other function in R, and you can give them other arguments. It just so happens that if I look at the bracket subset operator here, on a matrix, it takes I and j as its first and second argument, I being rows, j being columns, but then it can take a whole bunch of other arguments over here. Brackets aren't special, they're a function like anything else. You could imagine it's a function called subset with parentheses in them, and that the things we put inside those brackets are what you put in the function's parentheses. It just looks a little bit different. It's an operator in R. Okay. Weirdness. Yeah. This is something you will rarely have to do, but it's good to know about it in case you need it. Okay. So matrices can be like vectors, numeric, integer, factor, character, or logical, right? The thing is like vectors, matrices must have all of their elements be the same data type, okay? If I make a matrix here where I C bind together the numbers 1 and 2 and the 6th and first letters here, so F and A, the resulting matrix, you'll notice the numbers are now in quotes. This is because if you combine character data with numeric data, it all becomes character data. If you store numbers next to letters, R has to store it all as the simplest data type which doesn't lose information. With letters, the simplest data type which doesn't lose information is character data, so the entire matrix becomes character data. If I get type of it, this bad matrix here is character data, okay? So R will dynamically type or dynamically convert things to data types without asking you. Many other programming languages do not do this. If you're coming from a programming language that has strict typing like this looks blasphemous and terrible. But in R, it assumes you know what you're doing and just converts them without asking you. Just know that this is what's going to happen. Okay. So we can also give names to a matrix, and we can access it by names the way we can access vectors by names. So I'm going to assign row names to this matrix. I'm going to assign column names to this matrix. So this is something about matrices. Matrices do not just have names. They have names for each index in them. That is, they have names for their rows. They have names for their columns. If I then display this matrix, it has the same data right here, the 1, F, 2, and A, but now it has dimensions up here which have column names, and it has row names over here. I could subset this vector over here. Let's say that I want bad matrix, give me only the bigs row, this one, and it will return to me 2 and A, the appropriate row. So I've subset this by name. I did drop equals false here, it remains a matrix. If I didn't do drop equals false, it would lose the row names, okay? Here's a question. Can we have matrices with more than 2 dimensions, or are we limited to rows and columns? Once something has more than 2 dimensions, in R, it is not a matrix, it is an array. Arrays have an arbitrary number of dimensions. There's no limit to how many dimensions an array can have. Typically, you will rarely see people use an array with more than 3 dimensions. 3 dimensions is basically, imagine taking in a whole bunch of square matrices and then stacking them deep multiple matrices so that they have a depth as a dimension. But you can have 4th, 5th, 6th, 7th, 8th dimensional arrays if you need them for some purpose. In more complicated math in R, underlying some statistical routines, high dimension arrays are pretty common. One nice thing about arrays is math is very fast over arrays in R. So sometimes it's easier to work over an array than, say, a list of matrices. if you ever have to do it, arrays are actually pretty easy to work with.
And Chuck, quick question just about terminology. So we have columns and matrices and data frames.
Yep.
And I think of columns as just columns of data, and then matrices are combinations of columns and rows.
Yep.
And then how is a data frame? Is a data frame then the same thing as a matrix, or how are those different?
No. And so we're going to get to data frames here in a minute, but basically data frames look like a matrix, but they are filled with lies. They are not a matrix. They are instead a list object. They have columns, and they have columns and they have rows, but they only appear to have rows and columns. In reality, what a data frame is a list where each element of the list is a equally lengthed vector. So all the vectors in them must have the same number of elements, but they are in fact a list. So the big difference between matrices and data frames is every element of a matrix must be the same data type. But you'll notice in data frames, every element of a given column needs to be the same data type, but not rows. This is a hint that they are different from matrices. And it's actually because the columns are vectors and thus must have the same data type, but the rows don't actually exist. Data frame rows are not something that exists in the data frame. If you subset to rows in a data frame, what it actually does is it pulls out basically each element of the component vectors and returns it as that, but it will actually return it as sort of a weird data frame object. Data frames are a totally different type of data, which do not closely resemble matrices. They lie to you and pretend they're matrices, and we can actually use matrix subsetting on them, but they're not a matrix. We will call their variables in a data frame a column for convenience, but in reality, they are list elements of the data frame, and we're going to play with it here in a bit. Okay. Yeah, data frames are actually, they look really straightforward up to this point. You're like, oh, data frames are easy to work with. It turns out they're like one of the weirdest data types in R. They just don't seem like it. Okay, so matrix arithmetic. So matrices are the same dimensions. If you do math on them, they will do element-wise or entry-wise math using normal operators. So if I say, so I'm just doing C bind, C matrix, and D matrix to show you what these two matrices are. So C matrix is this first 6 elements, D matrix is this 6 elements over here. If I say 3 times C matrix divided by D matrix, what it's going to do is it's going to take the first element of C matrix, multiply it by 3, and then multiply it by the first element of D matrix. So that is 3 times 1 divided by 1 is 3. Then it's going to do 3 times 3 is 9 divided by 2 is 4.5. It's not doing matrix algebra on these things. It is just, if you imagine lining up each element with its corresponding element in each matrix, this one with this one, this one with this one, and then doing those operations straight down those matrices. Same thing with this 3, it's turning this 3 into a matrix of 6 3s of the same shape as these matrices and just going down the elements. This is just like doing vector-wise addition, multiplication, subtraction, all that. Okay. So if you want to do actual linear algebra operations on matrices, you have different functions to do those. So first, if you want to transpose a matrix, there's the function T. You know a function in R is really important and fundamental in the language when it is a one-letter function. This is a statistical programming language, so transposition is just T. Transposition happens constantly in every imaginable statistical operation, so it is a T. Okay, so if I wanted to transpose matrix C, I could say E matrix is the transpose of C matrix. What transposition does is it just flips your rows and your columns, right? Nothing special there. The rows before, the columns before, this was column 1, column 2, column 3, this was row 1, this was row 2. You could imagine it's flipping them diagonally. So before this matrix was this matrix here, you could imagine that the 5 is going to move down here. You'll see the 5 move down to there. It's kind of flipping them on their diagonal. Okay, standard linear algebra type operation. To do actual matrix multiplication, that is not entry-wise multiplication in R, you will do percent multiply percent. Looks like the other operators we've used. If I say F matrix is equal to multiplication of D matrix and E matrix, now we get our proper matrix product here. 22, 28, 49, and 64. D matrix and E matrix must be conformable arguments, proper linear algebra. If they're non-conformable, R will scream at you and say, learn to do a linear algebra, okay? So if you're not familiar with linear algebra, which is a class I do not require for this class, it's okay to sing the Meow Mix song and ignore all the things I'm doing talking about linear algebra. But if you do know it, these things are really useful for doing any kind of operations you might want to do on your matrices. So here's more examples of those sort of linear algebra type operations. If you want to solve for a matrix, okay, if you have an invertible square matrix, I could say take F matrix, solve for it, G matrix, and now I can get the inverse of that matrix. So you can give matrices to R, make it take their inverse. Solve gives you the inverse. And you know that this inverse works because I could take F matrix here, multiply it, or linear, I should matrix multiply it by G matrix. And what should you get when you multiply a matrix by its inverse? Does anybody know? No mathy people here. You should get an identity matrix. An identity matrix is a matrix that has zeros in its off diagonals and 1 down its diagonal. This right here is not a 0. It is really close to 0. This is negative 3.5 to the negative 15th, right? So 15 zeros basically in front of this, and then negative 3, well, 14 zeros, right? Okay, this is called floating point imprecision in computers. The issue is that math, 1 second, so I'm catching some audio from somebody.
All of our
Mute, there you go. Okay, so what this is floating point imprecision in the math. What happens is that computers can only do math to a certain level of numerical precision, okay? So instead of getting exactly 0 here, because it can't do, like, it doesn't divide evenly, it ends up getting really close to 0 and spitting out a non-zero value, okay? This is a case where maybe this calculation resulted in something with an infinite number of decimal places, repeating numbers or something. R can't display them all, and it doesn't know how to get them on, like, it doesn't round them or anything. It just gives you this level of precision, okay? This is a reason why if you do mathematical operations on things, you do not want to test if they equal a specific value. You instead want to test if they are close to a specific value, because computers cannot calculate exact values for many mathematical operations. They basically can't store enough decimal points to do it. They'll stop at a certain number. Okay, this can cause a huge headache in certain types of operations. If you do a lot of like hard math with computers, this is actually a fundamentally massive problem in computing, but for most of us, it's not really that big a deal. Just know it happens. Okay, so if you want to extract a diagonal of a matrix or make a diagonal of a matrix, such as an identity matrix, if I say diag2, it will create a 2 by 2 identity matrix with 1s on the diagonals, 0s in the off diagonals. Likewise, if I give a matrix to diagonal, it will extract the diagonal elements of it. This is something you probably won't have to do too often unless you're writing statistical routines by hand, which you probably will do in some CSSS classes if you take them. Okay, do we have any questions about matrices before we move on to lists? Okay, so thanks for bearing with me on the most boring lecture of the term. We're still chugging along here. I promise it gets more entertaining next week. I think next week is when I use the Billboard Hot 100 songs of the year 2000. My era of music. We're gonna have a good time next week. Okay, my boy Enrique's on there. It's gonna be good times. Okay, so what are lists? Okay, lists are a weird object in R. They are an object that can store multiple types of data in the same object. You create lists with list. So I'm going to create my list here. List is going to be equal to, the first element is going to be named the first thing. It is the numbers 1 through 5. The second thing is going to be a matrix of the numbers 8 to 11 with 2 rows. And the third thing is going to be the output from a linear regression of distance on speed using the car's data. So this list contains these numbers, a vector, this matrix here, and then the entire output from a linear regression model, okay? To R, each of these elements, it's interchangeable. The list can store whatever you want in here. Basically, all the rules for vectors and matrices are no longer obeyed here. You can put whatever you want in a list and it's perfectly happy, okay? And you'll notice in lists, the names are displayed like this: $, the name, $, the name. We've seen these $ name things before in data frames, the columns of data frames, because as I said before, data frames are actually lists lying to you and pretending to be matrices. They actually are the same structure as lists like this. Okay, so accessing elements of lists. You can access a list element by its name or number using double brackets like this, or a $ followed by its name. Note, if you use the double brackets, the name must be quoted. If you use the $, it must be unquoted. This is a weird thing, but this is how it be. Okay, if I say, take my list, subset to the first thing, I will get 1, 2, 3, 4, 5, because that's the first element of this list. If I say my list, first thing, I get 1, 2, 3, 4, 5. I could also numerically subset if I use the square brackets. I say my list, double brackets, 1, and I get 1, 2, 3, 4, 5. These are 3 equivalent ways to subset data in a list, okay? The thing is each one of these is easier to do in some different situation, so the flexibility is kind of nice. Sometimes it's real easy to grab things by name, but it's annoying to grab them by position. Say you don't know the order of things in the list or you want to rearrange it. Sometimes it's easy to subset like this because it's convenient and you want to pull one element out the way you pull one element out of a data frame, blah, blah, blah. Using this method is hard to use in loops and stuff, which we're going to learn in a couple weeks. Anyway, different ways to subset. Okay, so a good question, which usually would be asked if we were in person and people were raising their hands or scratching their heads or looking confused at me, why do you use 2 brackets instead of single brackets subsetting a list? So the thing is if you use single brackets to access lists, you will get a list back as the output. Double brackets will get the actual element stored in that part of the list, okay? So if I say something like, take my list, single bracket subset to the first thing, if I get structure on that, you'll see first thing comes out as a list of one element with first thing in it, okay? If I do double brackets, the first thing comes out says, oh, well, now it's an integer vector. This type of subsetting with double brackets extracts the actual vector. The single brackets extracts what is called a sublist of that element or whatever other elements we grab. The thing is here is that the way R works is that any function call in R can only produce a single object no matter what it is. It is not possible for R to return multiple objects with the same function call. If you ask for sub-elements of a list, 2 of them at the same time, because they would each be vectors or something like that, it would be asking you'd be asking to return multiple objects at the same time. R cannot do that. Thus, if you want multiple elements of a list at the same time, you subset with single brackets and then they pop out however many elements there are as a list containing all those elements. So the gist of it is, if you want multiple parts of a list, that is multiple elements, use single brackets to subset it. If you want a single element of a list, use double brackets and you'll get the actual contents of that element out. This is a fine distinction and it's weird. It's useful and it's powerful, and it's a constraint of the R language that only one object can come out at a time. It's a constraint of most programming languages, but a constraint here. But just know single bracket subset and double bracket subset for lists are not equivalent, and you need to think about which one you need to use. To get used to it, I recommend trying both on random list objects and seeing what happens. Okay. So subset lists can be, like I said, greater than length 1. So if I use single brackets and vector style subsetting of the sublist, there's too many subs in this sentence. You can use vector style subsetting to get a sublist of multiple elements. So if I say my list subset to element 1 and 2, the length of it is 2, and if I show its structure, you'll see this list is a sublist of the original one that has the first thing and the second thing in it, each of which is its own vector. Okay, so this is what I was talking about getting multiple list objects or elements out in one go. I can't do this with double brackets, but I can do it with single brackets. Okay, so why the hell would you want to work with lists if they already look this confusing? The reason is most useful objects that you will work with in R are lists or secretly lists. A good example is linear regression output. So if we remember, the third element of my list was the results from a linear regression. If I get structure on this object, you will see, even extracting it as the actual element itself, it is a list with 12 elements. The elements of this linear regression output are things like the coefficients, that is the estimates of the regression, the residuals, the effects, the rank. It stores the fitted values of the regression in it. You don't have to calculate them, they already exist in there. I forget what a sign is. And QR is a bunch of stuff having to do with the actual fitting of the model. That is things including, what do you call them? Basically, things from the result of the matrix operations, including like gradient characteristics and stuff. There's also a bunch of other things truncated down here. But basically, linear regression produces a list with a ton of stuff in it. If you want to extract some of these things from it, maybe you want to pull out the covariance matrix or something like that, you're going to have to be able to work with list objects. Okay, so you can use the names function on a list, and it will give you a vector of all of the element names in it, right? This should look familiar because we've used names on data frames before, because data frames are actually a list, and we were doing this exact operation. Okay, so we can see my list 3, which is that linear regression, has all of these different elements in it, which we could access by name. Okay, so yeah, like I've been saying, data frames are lists. Data frames are lists, except each element is an equal length vector. Okay, and you can see the similarity between lists we've worked with by running structure. I say structure cars, which is a data frame built into R. You'll see it says it's a data frame of 50 observations and 2 variables. So when we get lists, we don't see something like this. We just see the number of elements. Here, you can actually say there's a number of observations because every vector that makes it up must be the same length. This 50 is really just the length of all the vectors individually. But you'll see down here, this looks like when we got structure on the lists earlier. $ speed, it is a numeric vector, and these are its values. Just like a list, every element can have a different object type. The only main difference between a data frame and a list is that these elements, each one, must have the same number of elements in them. That is, in this case, 50. Okay? You'll notice, unlike a matrix, remember how I said before, if you do length of a matrix, it tells you how many elements there are in the matrix? Look what happens when I do length on a data frame. It says 2. This is just like getting length on a list. This data frame actually only has 2 elements. Its elements are the speed column and the distance column. Okay? It has 2 elements. They are its columns. If I do length on a subvector, that is cars, distance, the distance column in cars, length here is 50. This vector has length of 50, but this data frame has a length of 2 because it has 2 columns. Data frames are lists, okay? There's a hierarchy to them. Okay. When you do length cars $dist, does it take out the NAs? Nope. If there are NAs in there, they still count for the length of it because even though NAs are missing, if it's an NA there, it's an empty slot in it, and that object still has that much length. Okay, so like I keep saying, you can treat data frames like a matrix. You could say, take the cars data frame, give me the first row, all columns. Cars only has 2 variables, speed and distance, and this is the first row of it. I could say, cars, take the first through 5th row, give me the speed column, drop equals false, so it doesn't convert it into a vector, and we get speed, the first 5 elements of speed, okay? So this looks like matrix subsetting. Unlike lists, I can use matrix subsetting on a data frame. This works because data frames are made so that they must have an even length to all the columns, so you can treat them like a matrix. But this is sort of an illusion. They aren't really a matrix, it just allows you to use the same subsetting operations. Okay, so as a comparison, this is a base R versus a dplyr way of calculating the same thing. So let's say what I want is I want the mean of values in the mean rather of the education variable in the Swiss data set, but only for the values of education above their mean. So basically this is, imagine taking the top half-ish of the education variable and getting the mean for it. This would be the syntax to do this in base R. I say, take the mean, what do I want to get the mean of? The Swiss data set, where Swiss education is greater than the mean of Swiss education, and then give me the education column. The dplyr equivalent way to do this would be to say, take the Swiss data set, filter down to the rows where education is above the mean of education, and then summarize so the mean is equal to the mean of education. Okay? This is why we can use base R style subsetting of things when we want to, but it is not always the clearest way to do things. It's not always particularly readable. The dplyr way of working with data frames, what often involves more typing, tends to be read in a way that is a little bit more intuitive to a human than the base R way of doing it, okay? This is completely equivalent to this. Well, technically speaking, I would then have to pull the mean down here to make it 100% equivalent. Okay. So a little aside here, I want to talk about tibbles, the most adorably named object in the R universe. So tidyverse functions often use a type of data frame called the tibble. You can create these manually with tibble using the same syntax you would use in data frame. You can also convert data frames into tibbles using as tibble, okay? A tibble works basically like a data frame, but they display a little bit better by default in your R console, your R Markdown documents. So what they do, for instance, is they will truncate the output and they will also display column types. So if I take, for instance, the Swiss data set, select columns 2 through 3 and get the head, this is not a tibble. We see agriculture and examination. These are row names over here, because in the Swiss data set, the different provinces or cantons of Switzerland are listed as row names, okay? The equivalent output over here as a tibble shows agriculture, tells you it's a numeric variable, that is a double. Examination is an integer over here. It says it is a tibble data type with 6 rows and 3 columns, so it conveys more information. You'll notice here that I had to do something special. Over here, we have row names. A unique thing about tibbles is that tibbles do not have row names like a matrix. They have column names, but they do not have row names. If you have a data frame with row names, like the Swiss data set, you need to convert, if you want to keep those row names, you must convert the row names into a column. A way to do this would be to say, take the Swiss data set, and then select columns 2 and 3, and then as tibble, that is convert it to a tibble, and make the row names into a column called name, and then get head. There's now a name column here that was the old row names. So this is a philosophical decision done in the tidyverse. The gist of it was they decided row names are a stupid thing. I agree with this because row names are a weird type of metadata, okay? It makes a lot of sense to have column names, that is variables in a data set. It doesn't make any sense to have row names because row names, if they describe an observation, are a variable. Something that describes each row should be the contents of a column. something that describes a column as its identifier makes sense as a column name. So they have abolished row names, okay? Just know that tables don't have row names. If for some reason you need row names, such as you want to subset by row names, you can't do it with a tibble. Normally, instead of subsetting by row names in the tidyverse, you would subset by entries in a column like this name column. This is just a minor thing to know about, okay? Anyway, I talk about this because we will see a lot of tibbles in this class, and they're slightly different than a data frame. Syntax is mostly the same. Mostly you just lose row names. Okay.
Can I ask a quick question about that?
Yeah.
So, and this might be one example where you do need row names, but like if you have an outlier, for example, that like when you're doing like outlier analysis and it comes up with a particular row that is your like, is an outlier, the times at least that I've done it for like our basic statistics class has been by row name.
Yep.
Would you do it in a different way in a tibble?
Yeah, so the thing is that tibbles don't have row names, but they have row indices. So if you generate like if you find your outliers by the index of the row, then you can use the row index. The other thing you can do is you could create a column in your data frame that indicates whether something is an outlier or not, and then filter on that column.
Gotcha.
Things like that. Yeah, it's just like row names don't make any sense. Row indices make a lot of sense.
Okay.
Yeah, it's one of those things where it just they've kind of gotten rid of them. But yeah, I mean, if you need the row names, just make a data frame and use row names. But I mean, there's no, I literally have been unable to think of any situation in which a lack of row names has held me back in any way. So there might be some way that something very arcane, but normally it's just not necessary. Yeah.
Perfect. Thanks so much.
Okay. Next here. So an aside. This is a quick aside here for people with statistics training. So again, like I've said before, if this is something you're not interested in or don't know about, you can plug your ears and sing the Meow Mix song or something like that. But I'm going to talk very briefly about some stuff relevant to regression. Okay, so if you want to get fitted regression coefficients out of a model, you can do it with a little bit of list subsetting, right? So remember that my underscore list bracket bracket 3 was the output from a regression model. I can say my list bracket bracket 3 bracket 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 coefficients bracket bracket, I like saying bracket, and I will get the actual matrix in here of coefficients. This says take my list, go to its third element, and then of that third element of my list, go to an element named coefficients. Okay? I could then say I want to save the beta coefficient for speed, that is the parameter estimate for speed here. I could save this to an object called speed beta by saying, go to my list, bracket, bracket, third element, bracket, 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 coefficients element, bracket, bracket, single bracket, speed. So what I'm doing here is I'm going my list, its third element, an element of that named coefficients, and then this whole thing right here, which is what I display up here, is a vector. I can subset a vector by name just like this. So what I'm doing is I'm looking in this object here, getting the thing named speed, which is the number 3.932409. So this kind of shows you that with lists and sublists and all these things, you can just keep going down and down and down and down in your subsetting, right? You can burrow all the way down into this object, no matter how deep it is, with continuous one after another subsetting operators. Okay, this is how multiple subsetting works in R. Okay, so regression summaries. If you do summary on a linear regression object in R, you'll see that it produces output that looks like this. It provides a nice coefficients table with standard errors, t-values, p-values, the residual standard error, r squared, adjusted r squared, f stats, residual information, the original call used to generate it, all sorts of stuff like that, right? And I got this by saying summary my list 3 here, right? The thing is, which you probably don't realize if you've only casually used this before, is that this summary itself is actually a list object. It has a weird print routine that looks nice in your console, but it actually generates an object that looks different from what that is that gets printed in your console. I can say, take a summary of my list 3, the regression. This whole thing is the thing that I just printed on the last slide here. I could then subset to the coefficients matrix in this object, which is this thing right here. If I subset to that, what pops out is just that part of the summary. Okay? But what if what I want in here is I want to get, say, the standard error of the speed variable's estimate? I could say, take this summary of my list 3, browse down into this coefficients table, then grab the speed row and the standard error column, that's this column here, and I will get 0.4155128. This is a lot of subsetting to burrow way down into an object to get its standard error, but this is what you would do if you wanted to kind of manually extract things here, right? Okay, so here's an example of putting this to use. Let's say we want to manually calculate 95% confidence intervals out of this linear regression object, say to embed in our markdown document. I'm going to call this speed CI, so the confidence interval for that speed estimate. I can take the beta coefficient I extracted earlier, speed beta, and I can say add to this minus Q norm 0.975, Q norm 0.975. These are the quantiles of a standard normal distribution. Negative Q norm 0.975 is equal to 1.96. This is just me multiplying the standard error of speed by minus 1.96 and plus 1.96, which if I add or subtract that from speed beta, gives me the confidence interval on that coefficient, calculated directly from the information in that regression summary. I'm going to assign names to speed CI of lower CI and upper CI. And then I could include that in a markdown document. I could say, and write this text right in my markdown document, a 1 mile per hour increase in the speed variable is associated with a backtick R round speed beta 1, so rounding the beta and speed to 1 decimal point, foot increase in stopping distance with a 95% CI of the lower value of CI and the upper value of CI. The text you would see in your document would be a 1 mile per hour increase in speed is associated with a 3.9 foot increase in stopping distance with a 95% CI of 3.1 and 4.7. This is how I embed estimates and confidence intervals inside my journal articles. So I will extract them directly from the model object. So if I do things like filter different rows and all my models update, the text in my actual article will update for me and I never have to modify any values, right? So extracting these things right out of the object can be kind of handy, especially if you're working with relatively complex things. This is also good if you have like dynamically generated reports, like maybe you have something hosted on your website that just dynamically updates with data every single day. It can actually read out new parameter estimates, change the text and everything on the fly, and you can extract them out of these deep and complex objects using a little bit of subsetting that we've learned today. Okay, so that's a complicated example. You might use some of this if you do the harder of the 2 homeworks that are offered this week. Okay, so some practice stuff, talking about homework real quick. So at this point in the class, this might be a good time if you want to brush up on some R fundamentals and get a different view on these things. This might be a good time to try out Swirl in R. So what Swirl is an R package that will run interactive tutorials in your R console in RStudio, okay? So what you do is you can do install.packages swirl, load the library, do swirl, and then it will pop up menus and you can say, I want to do this tutorial and run through them. For example, you might do the basic R programming tutorials here, pick one, follow the directions, okay? If you want to exit swirl because it kind of takes over your R console, type bye and it will quit it. Anyway, tutorials 1 through 8 in R programming are appropriate for where we're at now in the class. So if you feel like you're kind of uncomfortable, sort of some kind of the basic R programming and stuff like that, or if you want to experiment with the things we've looked at so far, these are all really great tutorials. Another thing you might do is go to and check out RStudio primers, which I do have linked off the website, or you can just Google RStudio primer. Those are interactive cloud-based tutorials that also tend to have like lecture videos sort of attached to them to quickly go through R concepts. Okay. So This is the first week that has 2 homework choices. So actually, this might be the only one right now. I think I removed the harder homework from a later week. Anyway, there's 2 homework choices this week. There is something I call data structure practice. This is the less advanced homework, which most people do. This here, you will fill in an R Markdown template file that will walk you through creating, accessing, and manipulating data structures. The way this document works, and it's important to follow these instructions, I can't emphasize this enough, do exactly this. You will enter values in the Markdown document, 1 value at a time, and knit the document. Knit after answering each question. If you get errors, you'll want to check to see if undoing your last edit solves the problem. So the idea here is this is an assignment that is self-grading. It has code embedded in it that will check the values you input for each question and tell you if they're right or they're wrong. If they are wrong, it will attempt to tell you how they are wrong by being like, I think there's a wrong value here, maybe it's the wrong length, something like that, okay? It's really hard to write a homework assignment that grades itself and account for every possible problem that might arise, but this one has been doing a pretty good job in the last couple of years. Let me know if you run into any errors, but the main important thing, you answer it 1 answer, knit the document. At the bottom of the chunk, it will check your answers. If it says good job, go to the next answer, okay? The second and more advanced one is not an automatic graded assignment. It is instead a template still, but you just sort of walk through it. This one is one manual linear regression that will walk you through doing linear regression by hand, kind of, that is in doing the math yourself, and comparing it to the built-in LM function. This includes a little bit of an introduction to simulating data, creating and modifying data structures. Again, you'll want to knit after each answer. It doesn't check the answers, but you just kind of want to make sure you're going right. This one is long. Both these assignments are long, so start a little bit early on them. Definitely shoot me up on Slack and stuff like that if you're running to help. And this is the first week where we in lab will walk through the entire homework problem set. So if you get into trouble with this stuff, or for instance, you don't have a lot of time because we're coming to the middle of the term, come to lab and we will do the entire thing. I will make you guys give me the answers, but we will still do the entire thing. Okay, if you have questions, hit me up. That is it for today. Got anything for me?
Chuck, just a very basic question about when we import a data set, say just an Excel data set into R, it then becomes a matrix or a data frame, or I'm still a little bit confused on data frame. Okay.
Yeah, almost any function that loads in a data set is going to load it in as a data frame. Both base R and more advanced stuff will load in as data frames. So and that's just because they fully expect that different columns will have different data types. Yeah. And we're actually going to get into pretty deep into talking about loading external, well, not super deep, but we'll get into talking about loading external data. Next week is when we do loading data and tagging data. Yeah. Okay, well, if nobody's got anything else, then I will see folks on Monday, should you choose to show up to lab. Good luck on the stuff. Shoot me questions. See you next week.
Thanks.
Bye-bye.